agree very much. I could
Hello.
Sir, good morning, sir. Sir.
Yes, sir. Hello,
Sir.
Dr. Mat.
Sir, hello, sir. Sir, we'll start in 2 minutes, sir. Exactly by 10 we'll start, sir.
Okay, I'm hearing a lot of echo.
Sir. Sir, shall we start, sir? Meanwhile, they'll change. Sir, shall we start, sir?
Yes, please do.
So, very good morning to all. So, welcoming you to everyone for this wonderful session. So, actually, we are very privileged and honored to have such a eminent speaker for our session. So, jointly, it is an DL from IEEE and as well as it is an AICTE FDP. So, without wasting time, now I request Mrs. Kalyan ma'am to introduce today's eminent speaker to the participants. Madam, over to you.
So, thank you, sir. Good morning, everyone. And I take privilege in introducing today's guest of honor, Dr. Vijay Kumar Mishra, sir. Dr. Vijay Kumar Mishra obtained a PhD in electrical engineering and MS in mathematics from the University of Iowa in 2015, and MS in electrical engineering from Colorado State University in 2012. While working on NASA's Global Precipitation Mission Ground Validation Weather Radars, he received his BTech in ECE from NIT Hamirpur, India in 2003. He is currently research scientist at the University of Maryland, College Park under the ARL ART IAMAS program. Technical advisor to Singapore-based automotive radar startup Hertzwell and Boston-based imaging radar startup Aura Intelligent Systems, and honorary research fellow at SNT Interdisciplinary Center for Security, Reliability and Trust, University of Luxembourg. Previously had research appointments at the United States Army Research Laboratory, LLP, Electronics and Radar Development Establishment, Defense Research and Development Organization, Bangalore, IAHL Science and Engineering, Iowa City, IA, Mitsubishi Electric Research Labs, Cambridge, MA, Qualcomm, San Jose, and Technion Israel Institute of Technology. Dr. Mishra is the distinguished lecturer of the IEEE Communications Society in the year 2023 to 2024, IEEE Aerospace and Electronic Systems Society in the year 2024, IEEE Vehicular Technology Society from 2023 to 24, IEEE Geoscience and Remote Sensing Society from 2024 to 25, and IEEE Future Network Initiative in the year 2022. He is the recipient of the IIT Premium Best Paper Prize in the year 2021, IEEE AES Outstanding Editor in the year 2021, US National Academy's Harry Diamond Distinguished Fellowship in the year 2018 to 2021, American Geophysical Union Editors Citation for Excellence in the year 2019, Royal Meteorological Society Quarterly Journal Editors Prize in the year 2017, Viterbi Postdoctoral Fellowship in the year 2015 and 16, Lady Davis Postdoctoral Fellowship in the year 2017, DRDO LRD Scientist of the Year Award in the year 2006, NITH Directors Gold Medal in the year 2003, and NITH Best Student Award in the year 2003. He has received Best Paper Awards at IEEE MLSP 2019 and IEEE ACS Symposium in the year 2019. Sir, it's an honor to us to have you among us, and we are delighted and grateful. Thank you, sir. I just hand over this session to Dr. Vijay Kumar Mishra, sir. Thank you.
Thank you. Thank you so much. Can you hear me very well?
Yes, sir.
Yes, sir.
Okay. Let me share my screen. Let me know if you can see my slides.
Yes, sir. Yes, sir. We can see.
Okay, great. Yeah, thank you very, very much for the invitation. And I'm very happy to be giving this virtual distinguished lecture of IEEE Communication Society, organized by the Hyderabad Joint Chapter and BITS Warangal. So today I'm going to talk about one of the most actively researched topics in past few years from the signal processing perspective, as well as from the wireless communications perspective, and that is joint radar communications, or also known as integrated sensing and communications, or ISAC. It is very difficult to capture the entire gamut of research problems in this particular area in just this roughly 1 hour lecture. So my goal today is to give you a brief overview first, including a historical perspective of ISAC technology. And then I'll follow it by some specific examples. And as we proceed in this talk, we will start with a very theoretical example, and then we will end up with a very practical example. So that should give you a good idea about why this problem is important, how the research is progressing in this area, finally leading up to an entire spectrum of problems in theory, in practice, in hardware, and so on. So normally I talk about a little bit about my background, but I see the organizers have already given a very detailed biography of mine. So I'll skip that part, but I'll just underline that apart from my role at Army Research Lab and Maryland College Park, I'm a technical advisor of these two very promising startups. First is Hertzwell, which is based in Singapore. It is Asia's first automotive radar startup for self-driving cars. And second is Aura Intelligent Systems, that is based in Boston. They work on 5G imaging radars, which is very much related to the topic we are going to discuss today. That is the use of 5G waveforms for sensing applications. My broad research interest is in radar, and I explore its connections with signal processing, electromagnetics, communications, and remote sensing. I would like to acknowledge a number of my collaborators and colleagues whose collaborative research is going to feature in today's talk from ARL, from University of Luxembourg, and from the Industrial University of Santander in Colombia, as well as the National Academies of Sciences, Engineering, and Medicine, which is based in Washington, D.C., and a U.S. Army Research Lab for funding this research. In my talk, I like to include some snippets from my favorite science fiction TV shows and movies, just to keep things interesting, where the characters are discussing radar. Because that is one of my primary interests. And sometimes it may or may not be related to the problem that I am presenting. Okay, I hear some interference. So
sorry, sir, we are looking at it.
Yeah, so I like to include these snippets where the characters are discussing about radar. May or may not be related with the exact problem I'm discussing, but the one that you see on this particular slide is quite relevant to our discussion today. So this scene is from this very popular Apple TV Plus series, For All Mankind. Which is about a bunch of NASA scientists, and it is based in 1960s. It is set in 1960s. And in this scene, these two scientists, they are discussing the interference from solar flares because of heightened sunspot activities. Because of that radiation, the interference it causes to the Earth-based communications network. So apparently it can jam the communications networks for quite some time, and it is difficult to make a connection during the time when there is a heightened solar flare activities. Indeed, if you go back to 1960s, there used to be an IEEE journal, IEEE Transactions on RF Interference, where a number of papers that were published around that time in that journal were indeed about this problem. That is the effect of solar flares on the communications, the communications functionality for those networks that are operated from ground. So for example, this is a sample paper from 1963 published in that journal where they're discussing how the solar activity can interfere with the communication. So this is an example of natural interference. Today, we are going to discuss man-made interference. That is interference from other emitters like radar, navigation systems, and so on communications and vice versa. So clearly, there has been some work that has been going on in the domain of RF interference for past few decades. We saw these papers from 1960s, and then there was also some work that happened in 1970s. But a lot of work in this particular area of joint radar communications, and we'll see in a bit what it is about, has really kicked off in past 10 years. So the question is, while this problem of interference from radar to communications, etc., was known for many decades, what has changed in past 10 years? So there are several driving factors, but I'm going to discuss two major factors that affect this research and continue to shape the direction of AICTE research as of now, as we speak. So the first motivation comes from the communications industry. As you can see from this graphic that I have taken from industry sources, the current trends in wireless communications industry tell us that the number of mobile connections or the devices that are connected, that has already reached some 50 billion devices, and it is rising exponentially, dramatically it is rising. Because of so many devices that are being connected, a lot of data are being exchanged between those devices. And currently, it is very difficult with the existing cellular communications networks that we have to sustain these kind of data rates and to allow connection of so many devices. Apart from this, there is also demand from customers, from the wireless communication service providers, to provide them very high quality futuristic wireless services that can include gaming, infotainment, and so on. And all of these services, they also require very high data rates, which current sub-6 gigahertz conventional communications networks are unable to sustain. So how can we meet the demand of these high data rates that are expected of the future 5G or 6G networks? For that, we turn to the Shannon's famous capacity formula as a guide, which tells us that the capacity C, which dictates the data rate, is governed by three factors. First is the lowercase n, which is the number of orthogonal or non-interfering resources. It could be the number of time slots, number of channels, frequency channels, number of antennas on the transmit and receive sides, and so on. Second factor is the signal to interference plus noise ratio, or SINR, but you will have to increase SINR a lot to see any appreciable increase in capacity because they have a logarithmic relationship with each other. So we come to the third factor, that is W, or bandwidth. Now, obviously, they have a linear relationship, C and W. So wider the bandwidth, higher will be the capacity. But we cannot allocate bandwidth arbitrarily to just one application. That is because the electromagnetic spectrum is a scarce natural resource. Everybody wants a slice of that spectrum. So it is something that is rare and has to be used judiciously. As you can see from this graphic on the bottom right, which I've taken from Ericsson's white paper that was published in 2022, currently the conventional cellular communications range is in the sub-6 gigahertz part of the spectrum. That is where we have been operating for a while. And now the push is to move towards higher frequencies in future communications networks. And one of the major factors behind that is to access wider bandwidth. So wider the bandwidth, as you can see from that formula, we have wider the bandwidth, we have the better capacity or higher the capacity. So if you move to the higher part of the spectrum where, depending on which country you are in, you can have anywhere from 4 to 7 gigahertz of unlicensed bandwidth, because those are not yet allocated to any particular service provider in many countries. So people would like to move to millimeter wave or the so-called sub-terahertz range. That's one way to access wider bandwidth and meet the demand of higher data rates in future networks. In fact, this contest of wider bandwidth is also not new. As you can see from some of these headlines I've taken right from 1980s to as recently as 2020s, industry players or wireless service providers, they have been asking for wider bandwidth from government for quite some time. But it is difficult to manage the expectations and demands of all the service providers because we cannot allocate this bandwidth to just one player, one industry player. We have to satisfy so many players together, and we have to think of a better way to allocate the bandwidth. Second motivation for AICTE research comes from the radar industry. So we saw what is happening in communications industry. Now let's look into the radar industry. And mainly in radar industry, the particular industry segment that is driving this is the automotive radar industry. As you can see from this graphic, modern autonomous vehicles, they are highly sensor driven. Each one of the vehicle is fitted with several sensors, GPS, LiDAR, cameras, radar, ultrasonic sensors, and so on. And the goal of these sensors is not only to guide the driver in a crowded or traffic or challenging traffic environment, but sometimes also to monitor the general health of the car. So we have sensors for monitoring air conditioning of the car or sensors for tire pressure and so on. Sometimes we also have sensors that can monitor the physiological behavior of the driver or other occupants. So for example, we have in-cabin sensors that can measure the heart rate or respiratory rate of the drivers and passengers. So these autonomous vehicles, they are all sensor driven. If we focus on those sensors that are used to impart autonomy, then chiefly three sensors are common. First is a high resolution camera, which provides a very good visual. But when there are low visibility conditions, for example, at night or in the presence of rain or snow, then the performance of camera is not that good. Also, it does not measure Doppler velocity directly because it measures it indirectly by looking at the change in the movement of other vehicles across different frames. So it's not a direct measurement. If we are looking into self-driving cars, the vision of self-driving cars means you have to be very accurate in sensing your environment. So we move to the remote sensing based sensors like LiDAR and radar. LiDAR operates in the optical range of the spectrum, where the bandwidth is very high. People who work with radar or LiDAR or remote sensing related signal processing may recall that wider the bandwidth, the transmit bandwidth of the sensor, higher is the resolution. By resolution, we mean the ability of the sensor to discriminate two very closely spaced targets. So LiDAR operates in optical range. It has extremely wide bandwidth, and hence it has very high resolution. The problem with LiDAR is that it's a very expensive sensor. It's not a cheap sensor. So we come to radar. Radar is all-weather sensor. So unlike camera, doesn't matter whether day or night or in the presence of rain or snow, you can still get good measurements with radar. And it operates on Doppler principle, so it measures Doppler velocity directly. It is also a low-cost sensor. The problem with radar is that it has limited bandwidth because it operates in the microwave part of the spectrum. So unlike LiDAR, it has lower resolution. The only way to increase the resolution of radar is that we allocate more spectrum and more bandwidth to radar. But we have already seen in the discussion on communications industry that it's not possible to do that because spectrum is limited natural resource. As you can see from this, another headline that I've taken from just this year, and I have blurred out the name of the vendor for other proprietary reasons here, that there is one very famous almost autonomous car here in the US, but it does not use radar. It operates completely on camera. And because of that, there have been quite a few accidents in low visibility conditions because camera doesn't work in low visibility conditions. So we have to resort to something like radar or LiDAR, but then we also have to balance the cost of the sensor with its performance. So radar is the sensor of choice, but then we have to allocate more bandwidth. Apart from this, we also have the concept of modern cars being connected with each other. They're supposed to communicate with other vehicles, with satellite, with traffic infrastructure, and so on. And because of this connectivity, they generate a lot of data, which the current sub-6 gigahertz technologies for short range like DSRC or CV2X, they are unable to sustain those kind of data rates. So we noticed in the I'd remarked this in the communications industry discussion that if you want to have higher data rates, then again you have to resort to wider bandwidth. So everywhere we see that wider bandwidth is necessary for better communications performance as well as better radar performance. So both of these industries, they have been competing with each other. So autonomous vehicles, they need wider bandwidth for both reasons. If they want to stay connected, and second, if they want to have a higher resolution, that is accurate sensing. This limited bandwidth is an impediment for several systems. And that's why everyone wants to move to either those parts of the spectrum where they have higher wider bandwidth available. But then again, there are just so many players that we are unable to satisfy each one of them. So what is the solution forward? Before we move into the solution part of this problem, let's look into the current spectrum allocation, how it has been distributed so far. As you can see from this table, currently pretty much every IEEE radar band has a coexisting communication service. And this problem is becoming only worse with new communications and radar applications coming up. And as a result of which the government service providers, they are forced to allocate more bandwidth or parts of the spectrum to those new applications. Now, this problem is not just limited to radars or communications. Here is a headline from 2022 when FAA, which is the Federal Aviation Authority, asked, and this is FAA manages the airports and comes up with the regulations for airlines here in the US. FAA asked Verizon, which is a communication service provider, to stop transmitting its 5G frequencies near the US airports. The reason being, it was Verizon's transmissions were interfering with this device that is called the C-band altimeter that US airlines have been using for decades for landing and takeoff. So it is not even a radar, it is a different device, but even that device was receiving interference from communication services. And this led to a court case. So it also has legal implications. A second court case was in 2021. Here is the headline. When FCC, that is the Federal Communications Commission, the body that allocates spectrum across different industry segments, they decided to allocate slivers of sub-6 gigahertz spectrum to unlicensed users. That means anyone could transmit in that part of the spectrum. Now, sub-6 gigahertz is a very crowded part of the spectrum. Every single frequency is precious there. No one wants to lose access to any frequency in sub-6 gigahertz. But when FCC allocated it to unlicensed users, then AT&T, which is another service provider, they sued FCC in US courts, contending that this will interfere with the services that AT&T provides. So that was another court case. Apart from the fact that these devices are getting affected, you can see some other headlines here where the radio astronomers are complaining about interference from satellites that is affecting their clean sky observations. Or meteorologists are complaining about interference from Wi-Fi because they are unable to very clearly see the storm patterns because of that interference and so on. So recognizing the technological, legal, and policy issues of interference in various parts of the spectrum, DARPA, which is the defense funding agency here in the US, they launched about 12 years ago a program called S-Spark, that is to develop spectrum sharing technologies for S-band military radars and S-band military communications. Later on, National Science Foundation, another funding agency here in the US, expanded these kind of investigations across all bands, not just S-band. Now they're studying it in all bands, and they have launched several of the programs, some of which are listed on the slides, like SWIFT, NERDS, PAR, Spectrum X, and so on. So now this problem has become very important, and a number of government agencies, industry players, and academia and researchers, they are involved in studying this problem. All right, so now with that as a background, let's look into what kind of solutions are available if two devices want to share the same part of the spectrum, but without interfering with each other. So I'm leaving out some of the older solutions in this area in this lecture. I'll focus just on what has happened in past 10, 12 years since the launch of S-Spark program. So if I have to broadly classify the progress so far in spectrum sharing solutions, then here is a very broad classification. And this figure is from one of my signal processing magazine papers, very popular paper published in 2019. So what it shows here is that depending on whether the transmitter or receiver, they are shared between radar and communications, you have these 4 types of designs. First is when neither the transmitter nor the receiver is shared between radar and communications. So both of those systems, they transmit independently. Obviously, this will lead to interference at their respective ends. And most of the innovation there is only limited to the receiver signal processing on how to manage that interference. So that approach is called spectral coexistence. That is figure A. This was very popular with some of the traditional systems. Now, for the new systems, we would like to change both the transmitter and receiver. So in that case, if both transmitter and receiver are shared between, or even one of them is shared between radar and communications, then that approach is called co-design, spectral co-design. So this is based on the sharing of the hardware. But as I mentioned earlier, this is a very broad approach. Clearly, there is a lot of more work going on in this area, and we have several different approaches that have come up. So if we go into a little bit more detail, then here are the more classifications of AICTE topology. So recall AICTE is integrated sensing and communications. We also call it joint radar communications. So we saw one classification based on hardware. Now based on waveform, you can have another classification. Waveforms for radar and communications could be separate. It could be the same waveform and so on. Based on the location of transmitter and receiver, if both of them are at the same point, then we have co-located. If transmitter and receiver are not on the same platform, or there are multiple transmitters and multiple receivers, then you can have multi-static or distributed configuration and so on. Although in joint radar communications, we are interested in optimizing the performance of both radar and communications, there could be some cases where we are interested in optimizing the performance of radar while accepting some deterioration in the performance of communications. That approach is called radar-centric AICTE. Vice versa, you also have communication-centric AICTE. Another interesting approach in this is the opportunistic AICTE. So opportunistic AICTE is the case where we don't want to change an existing infrastructure. For example, I may have a radar infrastructure already available to me. I don't want to make a lot of changes in that hardware, but I want to use that hardware for communications. So that is called opportunistic AICTE. So you can also have vice versa, and we'll see one example today of opportunistic AICTE as well. And then depending on what part of the spectrum you are using, what is your specific hardware and so on, you can have several of these specialized AICTE topologies. Now, it is not surprising that we have so many AICTE designs. The reason being, we have various applications of radar systems and we have various communications protocol. And whenever you want to share the hardware or share the spectrum between one of those radar applications with one of the many communications protocols, usually it leads to a new system or a new solution. And that is the reason why so much AICTE literature is coming out. In fact, about 15 IEEE societies have published AICTE literature so far, and this is not just limited to IEEE. It ranges to International Union of Radio Science, American Meteorological Society, ITU, and various other professional organizations as well. So the problem is really pervasive, but at the same time, for scientists and researchers and students, it is a great opportunity to work on some of these challenging problems. All right, so we covered the historical context, motivation, what are different challenges, and so on. Now, in the remaining time, let's look at one example each. So we'll look into one example of spectral coexistence, then one example of spectral co-design where we'll look into the automotive AICTE, that is for self-driving cars. And if time permits, maybe I would like to provide maybe another example. Similarly, I'll end this with an opportunistic AICTE example. That means we have some hardware which works for one functionality, but we also opportunistically use it for the second functionality. And as we move from spectral coexistence to opportunistic AICTE, we'll also move from a very theoretical signal processing example to a very practical example. So that covers the whole spectrum. Let's start with the spectral coexistence. And here I have chosen the problem of dual blind deconvolution. So if you recall spectral coexistence, most of the innovation is on the receive side. We are not that much interested on the transmitter side because we don't have much control on the transmitter. What is the problem of dual blind deconvolution? To understand this, let's have a look at how standard radar and communications work. In a conventional radar, we transmit the waveform, so we know what waveform it is. That waveform then interacts with a target of interest, which could be either aircraft or tanks, or could also be human beings. And when the signal is reflected from those targets back to the receiver, then the received signal is the convolution of the transmit signal and the radar channel or the target profile. Out of these two things, that is the channel and the transmit signal, we have the knowledge of the transmit signal. With that as a knowledge, we try to solve this problem where the unknown that we would like to estimate is the radar channel. This is called deconvolution. Now imagine if you don't know even the transmit waveform, then both are unknowns, the transmit waveform as well as the radar channel. In that case, just by looking at the convolution product at the receiver to estimate these two unknown quantities is a very classical signal processing problem that is known as blind deconvolution. So that can happen in a passive radar where someone else is transmitting the waveform, or could be some hostile entity that is transmitting the waveform. That's why you may not know the waveform. In communications, a similar situation arises. In communication, it's the transmit signal that is unknown to us. Transmit message is unknown, and the channel is something that we estimate a priori. So standard communications, you will have the knowledge of the channel, and you would like to estimate the transmit signal. But in a vehicular scenario, where the channel is very dynamic because of the movement of vehicles, even if you estimate the channel, that estimate of the channel becomes outdated very quickly. And you would have a situation at the receiver where you don't know the transmit signal and you also don't know the channel. This is for radar and communications separately. In a coexistence receiver, both of these signals will be superimposed on each other. And that's when we'll have a problem of dual blind deconvolution. That is what this first equation here on the top tells us. So X, if with the subscript of R and C, so subscript R and C, they denote radar and communications. X is the transmit signal, H is the channel. So the first convolution that you see is for radar at the receiver, and second convolution is for communications, and the superposition of both of them is the received signal Y. Now, just by looking at Y, we would like to estimate all four unknowns. That means XR, HR, XC, HC. Normally, it is not possible because just by looking at Y, how can you find out all four? There will be so many combinations of all four that will match to same Y. These kind of problems are called ill-posed problems. That means you actually cannot uniquely solve them. They have many solutions. To uniquely solve them, in blind deconvolution literature, we resort to some knowledge of the structure of the unknown signals. If you know something about the structure, then you can solve them accurately. So this was our strategy in this work. This was published in IEEE Journal of Selected Areas in Communications Theory last year. Selected Areas in Information Theory, JSAIT journal last year. And our method to solve this was as follows. So we start with some channel models. For the communications and radar channel, we assume that they are delay Doppler channels. That means, let's say for radar, we assume there are L targets on the scene. Each one of the target is characterized by a complex coefficient alpha, which denotes the size and shape of the target. The unknown delay tau r. So tau r is directly proportional to the location of the target with respect to the receiver. And then Doppler frequency nu r, which is directly proportional to the Doppler velocity of the target. So it's a superposition model. It's a very classical radar channel model. For communications also, we assume Q paths and a similar delay Doppler channel model. For the signals, for radar signal, we assume it is a train of pulses, unknown pulses S, but we know how many pulses are there in a given observation duration. If you don't know how many pulses are there, even that can be estimated. But for the time being, let's leave that aside. For the communication signal, we assume it's a OFDM signal where we don't know the messages GP. Now you take all these four equations and put them in the first equation and then sample that equation. Then after a few pages of tedious algebra, we get this last equation that you see on this slide. In this last equation, we have several unknowns. So now we have some structure at least, but it is still, we have to go through a few more steps to solve this. And there are several unknowns. There are channel parameters that are unknown and both transmit signals that are unknown. And we would like to estimate all of these unknown parameters by just looking at the measurements Y. So we got the model, but we still don't have an algorithm to solve this. So how do we proceed next? We make we make the following observations. So we are going to use two primary tricks. For the channels, we assume they are sparse channels. That means there are only L targets and Q paths compared to the total number of samples that the receiver is going to sample. So the total number of samples is very high, but out of those samples, there are only L targets and Q paths. So it's a very small number. So if the channels are sparse, we'll see there is another trick that we could use to solve this. As far as the transmit signals are concerned, we put a mild constraint that they lie in a known low dimensional subspace. So usually flat spectrum signals, they qualify under this. This is also called the lifting trick in blind deconvolution literature. Now, you take this lifting trick, and again, after a few pages of algebra, we can write our received measurements Y in a compact form as this, where I'm using a linear operator, aleph R and aleph C, that is for radar and communications. And both aleph R and aleph C, they are functions of rank 1 matrices ZR and ZC. Now, ZR and ZC, these are rank 1 matrix that encapsulate all the unknown quantities that we would like to estimate for radar and communication. So if you estimate ZR and ZC, you get your unknown quantities. That is the idea. I would like to attract your attention on the structure of ZR and ZC. If you look into the structure of ZR and ZC, they have these complex exponentials. That is e to the power j2 pi and then some phase. Now, when we talk about complex exponentials, then you may know from trigonometry that we can write a complex exponential in terms of sines and cosines. So in other words, here, if we have to use a more formal language, we are dealing with trigonometric polynomials. Now, this fact will come very handy in solving this problem. We'll come to that in a moment. Normally, when you have a sparse channel or there is some kind of sparsity in the signal, then the way forward to solve it is using L1 norm minimization. However, here the sparsity is not straightforward. Here the sparsity is in two domains, that is the delay domain and the Doppler domain. Because of that, we cannot use L1 norm minimization. So we use a generalization of L1 norm, which is called atomic norm, which was proposed about 12 years ago. And so here we would use this generalization of atomic norm. However, there are two differences compared to the classical atomic norm. Difference number one, the atomic norm that we are going to use is multidimensional because this is a function of both delay as well as Doppler. Second difference is it's not only one atomic norm that we have to minimize. We have to minimize the sum of two atomic norms. That is ZR and ZC, their atomic norms. Radar and communications are together. So this problem is also called Soman minimization. That is sum of multivariate atomic norm minimization. So we write our primal optimization problem here that minimize the sum of two atomic norms subject to the measurements that we have made. Now, this is still not very tractable problem. To make it a little bit more tractable, we would look at the dual of this problem. People who may be familiar with optimization theory may recall that if I have only equality constraints, so these are equality constraints here, y equal to something, then in that case, if I write the dual problem, then by Slater's condition, strong duality holds. That means if I solve the dual problem, I also get the exact solution of the primal problem. That's what we are going to do now. We'll look at its dual. But to tackle that dual, we have to do a very quick diversion toward the trigonometric polynomials that I had alluded to earlier. So here we are dealing with trigonometric polynomials, but specifically we are dealing with positive trigonometric polynomials. And because it is higher dimension, it's positive hyperoctane trigonometric polynomials. So what is the property of these polynomials? So Professor Bogdan Dumitrescu from Tampere University, he wrote this beautiful book in 2007 on signal processing applications of PTPs, that is positive trigonometric polynomials. And the property of that polynomial that we will use is as follows. It says if I have a positive trigonometric polynomial here, that is Rz, where z is that exponential, then the coefficients of that polynomial Rk, I can parameterize them using a positive semi-definite matrix Q. What is the import of this result? Import is that I can use, if there is an inequality on this trigonometric polynomial, I can describe it using a matrix. So I can use a linear matrix inequality to describe this, and we'll see how this helps in solving the problem in a moment. Now, this was for a single dimension. The definition, you can extend it to multi-dimensional, multivariate cases. That's what we did in our work. So we will use the multi-dimensional version of this result that you see on this slide. Now, how do we use it? So we wrote the dual optimization problem. And if you recall, the primal had minimized, dual has maximized. Primal had equality constraints, dual has these inequalities on the dual of atomic norm. If you expand this inequality and take this expression that you see here on the right-hand side, then it becomes 1 minus this expression greater than or equal to 0. And if the left-hand side you expand, then that entire relationship is a positive trigonometric polynomial. Now we know from the previous result that I can replace this inequality with a linear matrix inequality. That is what I'm doing in the second equation. So although this looks complicated, the second equation, this is the result we wanted, because in optimization theory, this is what we call is a semi-definite program. That means now I can go to a computer and I can actually write a code for this problem. So far we did not have a SDP, but using these tricks that I described so far, now we can write an SDP. Fine, you write an SDP. How do you get the unknown signal or unknown channel? So we have very strong performance guarantees on these kind of problems. So once you solve this, you get two polynomials, one for radar, one for communications. And the result that we have derived, that is the proposition that you see here, says the following. After solving the optimization problem, you take both polynomials, you plot their absolute values in a delay Doppler plane, wherever that value is exactly unity, that is the location of your target or the channel parameter. So, of course, within some numerical precision. So we actually show through an experiment here where we are plotting the absolute value of both polynomials, one for radar, one for communications, and we are also zooming in wherever their values are 1. So the true parameters are green circles, and plus sign that you see, that is where the value of this polynomial is unity. Turns out they are on top of each other. So it's a very accurate recovery. So this is a very good theoretical example of how complicated signal processing for a joint radar communications can turn out to be, even though the problem may look very easy at the outset. There are several other variations of this problem. If you are interested, you can find more details in some of the papers that I have listed here at the bottom. For example, you can extend this to even higher dimensions in the presence of noise and so on. You'll find all those details there. Now that we have looked into one example, that is spectral coexistence. As I mentioned earlier, we would look into one example of coexistence, one or two on co-design, but I'm looking at time. We'll just look into one example of co-design, and then a very interesting example of opportunistic AICTE toward the end. So in spectral co-design, I've chosen the problem of automotive joint radar communications. That means the self-driving cars. So you may recall this diagram from earlier. This is a bistatic joint radar communication system. So here I have a red car, which is the transmitter, and transmitter for both radar as well as communications. And it is transmitting a common waveform that common waveform then gets reflected off from this blue car and intercepted by a common radar and communications receiver, which is the gray car. And the goal of signal processing at the gray car is to extract the location of this blue car or its Doppler velocity. That means it to function as a radar receiver, but to also decode the message that was sent by the red car. So it's also acting as a communications receiver. So this work appeared in Transactions on Aerospace and Electronic Systems Transactions, and it was the runner-up for IEEE Barry Carlton Award last year. So what did we do in this work? So recall in spectral co-design, we also work on the transmit part. Coexistence is only for receiver, but here we are also looking into transmit part. And then one of the crucial issues in the transmitter is to find out which waveform will be best for both radar and communication. So here we experimented with two waveforms. One is phase modulated continuous wave that is mostly used in radar applications. Second is OFDMA that is largely used in communications applications. PMCW has a good performance in estimating the range of the target. OFDMA has a good performance in estimating the Doppler velocity of the target. So first we wanted to see how do these properties they carry on in the joint radar communications mode. For that we derive what we call as ambiguity function of the waveform. People who may not be familiar with ambiguity function, if you, so here is a very brief primer. You take the transmit waveform, then you shift it in time as well as in Doppler and then correlate it. So that correlation is the ambiguity function. And its shape somewhat looks like a main lobe in the center and then lot of side lobes. So these are the ambiguity functions we derived for the joint radar communications versions of PMCW and OFDMA. And what we noticed through these ambiguity function is that the children waveform, they retain the properties of the parent waveform. PMCW JRC also has a good range estimation performance, and OFDMA JRC has a pretty good velocity estimation performance. Now, with that known, we want to check out how's the receive processing. That was the transmit, but now the receive processing. So for the receive processing, here is a more detailed version of that, but I'll just summarize this. If you're interested in more details, I'll be happy to talk about it. But here's the summary how this signal is processed at the receiver. So recall that signal is received by the gray car, and it's a common signal. So here is the four summations that you see on this slide. That is the received signal. There are a lot of unknowns there. There is range that is unknown, Doppler that is unknown, angle of arrival, as well as communication symbols. In PMCW JRC, you can estimate range and angle very well, but the Doppler and communications are difficult to estimate because after you remove range and DOA, then these two other parameters, Doppler and communications, they are coupled with each other. You cannot separate them. You cannot separately estimate them. So in our work, we suggest a way how to do that. So that is using multiplexing. You do not transmit the joint radar communications all the time. You, for some percentage of the coherent processing interval, you transmit radar-only frames. After that, you transmit joint radar communications, and that can help in breaking the coupling and estimating these separately. In OFDMA JRC, we have a very similar problem, but it is the Doppler that is estimated very well, but the range gets coupled with communications. Again, the solution is multiplexing. That means use some subcarriers of OFDMA for radar-only transmission and the rest of them for the joint radar communications transmission. Indeed, if you look into the system design of this joint radar communication system for self-driving cars, the receiver is very similar irrespective of what waveform you are using. So you have a radar processor, you have a communications processor. Once you remove the communication symbols from the radar processor, then it estimates the coupled parameter. Of course, the transmitter will be different. These are two different waveforms. The only common part in PMCW and OFDMA is the multiplexing. So multiplexing is common for both, but for PMCW, it happens in time domain. OFDMA, it happens in frequency domain, and so on. I want to end this segment by showing this one result, which shows us how multiplexing is very efficient in these cases. Since range is the coupled parameter for OFDMA, here I'm plotting the error in range with respect to SNR, that is the figure B. And then in figure D, I'm plotting the error in Doppler for PMCW because Doppler was the coupled parameter. Red curve that you see is the theoretical curve, that is the best performance. Now, when we don't do any multiplexing, then it is the blue curve. So at high SNR, you don't need multiplexing. So at high SNR, the blue curve merges with the red curve. But usually these kind of systems are low SNR systems. They are not high SNR. So at low SNRs, the divergence between the blue and red curve is high. However, if you do multiplexing, which is the gray curve that you see here, then it can bridge that gap. It can lower the gap between the theoretical performance and the practical performance. So it shows that this kind of multiplexing is actually essential. It's not even an option for in practice for most of these systems. All right, so I see I have probably 5-6 minutes left. So I want to jump to the opportunistic AISAC. So let me see. Can you see my screen?
Sir, sir, we're unable to see, sir. It's not sharing, sir.
Oh, okay. Do you see now?
Yes, sir. Yes, sir. Yes.
So the last thing that we would look into is the opportunistic AISAC. That means you have some hardware for communications available. You want to use it for radar. And the example that I've taken here is the weather sensing. So typically, we use weather radars to sense weather. But weather radars are very expensive. And there are many regions in the world where there are no weather radars. However, at many places, we have the communication satellites ground terminals. So the signal is coming from the satellite and coming to these ground terminals. So it is going through the atmosphere. Now, the amount of time it spends in interacting with the rain, that is proportional, that is reflected in the proportion of the attenuation that signal suffers. So if we know something about the attenuation of the signal, we can compare it with how much rain would have been present in the atmosphere. So that is the idea. Now, radars are not available everywhere, but communication terminals, as you can see here, there are 2 million of them worldwide. And just in Europe, there are 300,000. And even in India, there are quite a few. So the challenge that we had was that can we estimate rainfall R from the attenuation data? So here, all that we know is how much power satellite transmitted and how much was received. Received power is severely attenuated. The amount of attenuation is proportional to rainfall. Can you estimate the rainfall? So as I mentioned earlier, if we have radar, it is very accurate because weather radars are designed for estimating weather. But here we don't have a lot of information available. So since we don't have a lot of information, we turn to machine learning in this case. So the idea is that we will feed a machine learning network, a deep neural network, with data from the nearby radar in the training stage. And then in the prediction stage, we are going to feed the data from satellite and then see what kind of rainfall it can give us. So we started with this southwest region of Germany, where you can see we had about these some 30 terminals or so. And we trained them using LSTM network with the nearest German weather radar service data. And then this is the result. These two plots that you see are the results for just one terminal so far. So here what we see, the bottom plot is the instantaneous rain rate. So here the satellite link, that is our neural network output, that is in red. It follows the German weather service radar very closely. But instantaneous rain rate is not what meteorologists use. They use cumulative rainfalls or accumulations. So accumulations, if we are comparing, then you can see that as time goes by, the satellite link is lagging or the difference is quite big compared to the radar. So it's not very accurate. We want to improve this. But if we just continue with that kind of LSTM network, we feed the data for all the 30 terminals, and once we have this prediction, we generate a rainfall map. So here on the right side is what the German weather radar is seeing, that is accurate. And what our satellite network from deep neural network is giving is on the right side. As you can see, there is no comparison. I mean, all that is uh, comparable is a rough blob that you see here, the intensity of the storm and a broad direction, but there's no comparison in the pattern. So far from this figure, it is clear that there isn't a lot of useful information. So we did a lot of other iterations, but here we had access to just uh, 30 terminals. Then we got access to the data from France. Now, as you know, in deep neural networks, if you have more data, usually you will get a better result. So from France, we got access to 11,000 terminals, and then we trained our various types of neural networks. And here is the result we got. So here you can see that radar is on the left side and satellite is on the right side, and they match very well. So with more data, neural network output can match a lot. And here we are comparing every 3 hours the radar and the satellite link, and they match very well here as well. Here is a movie that shows you the comparison of radar versus the satellite link. So all these black dots that you see in the map, in the satellite accumulations, those are the location of the user terminals. And sometimes they go away, there is outage, but still the neural network is able to capture the circulation seen by the radar, the intensity of rainfall, and it's very accurate in estimating the rainfall. So with more data, you can actually do better. There's a very practical example of using communications infrastructure to complement the observations of radar. We also did this for Germany, and currently we are also looking into Switzerland and so on. So it's a very nice practical example. All right, so we looked into a lot of problems so far from practical perspective, from theoretical perspective, and so on. And in the beginning, at the beginning of this lecture, I had remarked that it is very difficult to summarize all kinds of problems in just this 1 hour talk. But if you are interested in looking into other architectures of ISAC, then I have provided quite a few references here from some of the other work that we are doing, for example, distributed or full duplex ISAC, various other waveforms of ISAC, and so on. Another thing that I wanted to remark on was that when you are sharing spectrum between radar and communications, then the security of military radars and privacy of communications users could be compromised. So there is a lot of focus on secure and privacy preserving ISAC, and we also have done some work. So here is another slide on some other trends that are emerging in joint radar communications and ISAC, and you can explore more by looking into these references. All right, so we have come to the end of this lecture. Now, at the end of the every YouTube video, there is like, share, subscribe. Now, this is not a YouTube video, but if you're interested in following more of my work, then feel free to follow me on LinkedIn at this handle. We have done a lot of work, and we had some books that were published last year and this year on some of these related topics. So I put the information about the books here, and we have some coming, some other books that are going to come up next year. And you can find more information, a lot more than what I've covered in these books. With that, I would like to thank you for being a very patient listener, and I'm happy to take up any questions you guys might have. Thank you.
Thank you, sir. Thank you. Participants, if you have any questions, you can ask, sir. Sir, actually, at the beginning, you mentioned that the data rate and bandwidth both are needed as high as possible for. So, how can we trade off between them, sir? As we need both as high.
Yeah, well, so capacity dictates the data rate, and capacity depends on those 3 factors: higher bandwidth, larger number of non-interfering resources, as well as higher SINR. But SINR increase a lot because they have a logarithmic relationship. So we can only play with either the bandwidth or the number of orthogonal resources. The number of orthogonal resources could be number of antennas. So the concept of MIMO communications is that with a multiplicity of antennas, you can have a bearing on capacity. And then there is bandwidth, but bandwidth is limited. If you want to allocate more bandwidth, then you have to look into these kind of technologies where you can share the bandwidth with other applications without causing interference.
Okay, sir. Thank you. Sir, in autonomous vehicles, if multiple vehicles are at the same position, if they are using same channel, so how can we mitigate the interference, sir? If they're communicating using same channels?
That is a very good question. I mean, in general, self-interference in automotive radars is a very big challenge these days. There are various methods how to deal with it. Each one of the vendors have their own bespoke technology. So one way could be you can use noise radars. So there is a noise look like code that you can modulate your radar waveform with. It's like CDMA, but easily generated code. But the code is unique to each radar, so you can separate it from other radars. That is one technique.
Thank you, sir. So participants, you can ask questions. Sir, actually, sir having very limited time. Sir, as most of us from faculty community, so could you suggest some research topics so that we can work it on it?
Yes, so all these, I mean, I can only suggest topics in my area.
Sir, yes,
So
sir.
into joint radar communications or AICTE, I mean, it's a minefield of various new research problems. Pretty much, I mean, these days I see every day I get Google Scholar alert for new papers in this area. So there's a very actively researched area. And I would encourage researchers who are looking for some challenging problems in signal processing and wireless communications to look into AICTE more. And it's very, very wide variety of problems are available.
Sir. Thank you, sir. Thank you so much, sir. So I personally know how much effort you put for taking this session, sir. So on from the Department of EC Bits as well as from IEEE Hyderabad Communication section, we are truly honored and privileged to have you, sir. So thank you, sir. Thank you so much for taking this session, sir. So it's such a wonderful session, sir. Really, our participants enlightened with your session, sir. So thank you, sir. Thank you so much, sir.
Yeah, thank you. Thank you for the invitation. And it's my pleasure to do this.
Sir. Thank you, sir.
Okay, all right. So I can end this session here.
Yes.
Okay. All
Yes,
right.
sir.
All right. Thank you and best wishes for your program today.
Sir, thank you, sir. Thank you so much.
Bye.
Bye. So, dear participants, the next session will begin in the evening only at the same time at 6:30 p.m. So, after this session, Karthik sir will share the link in the group. Okay, kindly fill it. Okay, once sir share the PPT, I will share it in the group. Thank you. Thank you, everyone.